Assalamu alaikum students. In today's lecture, you will learn about the differences between sigma and pi bonds, then formation of molecules under the heading of PBT, hybridization and sp3 hybridization under the heading of the structure of methane, ammonia or water will be discussed. Okay. Rahmanir-Rahim. Now here the differences between sigma and pi bonds is given. The sigma bond is formed by the axial overlap of the atomic orbitals. It can also be termed as the end-to-end overlap or head-on overlap of the two orbitals, which are partially filled, that contains only one electron in them, while the pi bond is formed by the sideways or lateral overlap of the atomic orbitals, which are partially filled. Now the sigma bond will be formed between that of the s to s orbitals by their overlap, or s to p orbitals overlap, or by p to p orbitals overlap among the three p orbitals, right? Now here the pi bond is formed by the overlap of only and only p orbitals. After formation of one sigma bond, then their p orbitals will overlap to produce the pi bond. Now here we have the sigma bond is stronger than that of the pi bond, which is a weaker one bond. This is due to the maximum overlap takes place in case of the sigma bonds, as they are the symmetrical one molecules are there, which will give the larger extent overlap, while in case of the pi bonds there will be the smaller overlap, or the smaller one extent of overlapping is there due to the regions which are present above or below the planes. Now here the molecular orbital is symmetrical in case of sigma bonds. The whole electron density or the electronic cloud will lie on the central axis. They are symmetrically present around that of the central axis, right? While in case of the molecular orbitals formed in pi bonds, the electron density will lie above or below the plane. The central region is the nodal region where no an electron density is going to lie. So there is a discontinuity of the electronic sheaf, right? Now here in the sigma bonds there is present, as they are the single bonds, so free rotation is present of the groups, right, which are attached by a single bond. While in case of the pi bond, pi bond is formed after the formation of one of the sigma bond, so that there will be the two bonds between that of the bonded atoms. There is a restricted rotation, not allowed they are to move freely. If they are allowed to move freely, the pi bond will break, right? And the next one is they can be these bonds, they can be present between the two atomic orbitals. Maybe they are alone or they are with that of the pi bonds, while the pi bonds will be formed when there is formation of sigma bond. After that they will be formed, right? The shape of molecule is determined by means of the sigma bonds around that of the central atom. Here you are familiar with the formation of the CH4 molecule, which holds 4 single atoms present in it. But if we consider that of SO3, there are present two bonds between sulfur and oxygen for each oxygen. Here one sigma and pi bond both are present. So pi bonds are, they are not giving the determination of the shape, but they are modifying that of the molecular shapes, right? The dimensions of the molecule, as the two bonds will be considered at the same direction, right? So that's one. Now this is all about the difference between sigma and pi bonds. Here this question is an important question, frequently asked in the exams. Now here under the BBT, as we have done the postulates in the previous lecture, here the formation of some of the molecules is given. It is a homonuclear or homoatomic molecule which is formed by hydrogen, as two of the atoms are similar in all respects, right? For this you must know the configuration of hydrogen. First, hydrogen having atomic number 1, it will give you the configuration, that is H1 is equal to 1s1. Must you have to write it, as the s orbital is present only, which is partially filled, so each hydrogen will contribute one of its 1s orbital, which is spherical in shape. Here it is given, the both of them, they will overlap to produce a sigma bond. This will be a maximum overlap and the electron density will lie on the central axis as it is given. So this is a sigma bond formation. It is the joining axis of the two nuclei. They are symmetrical molecular orbital which are formed over there. Actually, the identity of the atomic orbital is retained, although there is a overlap region, but still they have their identity retained. Right now, this is how the formation of the hydrogen molecules takes place. As I told you earlier, both atoms will lose energy to come at a compromising distance where the attraction between them is maximum, so they will give rise this sigma bond formation, and it is an exothermic reaction as energy is given out in it. Right now, here hydrogen to hydrogen, just one bond can be formed as there is present only one hydrogen with each hydrogen. Now here the next one is F2 molecule. It is also a molecule, a homoatomic molecule, or you can say it is the homonuclear one. Two fluorine atoms, they will link together. Here the configuration is given. Fluorine with atomic number 9. It is having configuration 1s2, 2s2, 2px2, 2py2 and 2pz1. Now here among these orbitals you can see there is just one orbital which is partially filled. According to the VBT, only this orbital will undergo bonding, right? So here two orbitals are mentioned here, which are the atomic orbitals which will overlap to produce a sigma bond, as it is a overlap which is taking place on the central axis by the head-on overlap. So this is overlap which is shown. Each fluorine will contribute its one of the electron present in its outermost shell in 2pz orbital. So they will overlap to produce a sigma bond. Right here, the formation of the sigma bond or the molecular orbital region, which is shown by the overlap of the two p orbitals, is given. Right now, here again the formation of sigma bond will occur between fluorine atoms, and only one bond can be formed between two fluorine atoms. This one is also, remember it, every time the bond formation is an energy releasing process. Here the chlorine molecule is mentioned. Again, it is homoatomic molecule, right? Chlorine with 17 atomic number. You can see in its 3p orbital, one p orbital is holding one electron. All the other are the pair. All the other orbitals, they have paired electrons. So there is only one orbital which will undergo bonding under the heading of VBT, valence bond theory. Here, three of the orbitals are mentioned with each chlorine atom. You can see, you can write them first separately as given in your book, and all the three are being mentioned according to their Cartesian coordinate dimensions, that is x, y and z. Here one of them is having the unpaired electron while the other two will hold the paired electrons with each other. Here it is given that the one overlap which takes place over there is this one overlap. This overlap shows you it is the overlap which is going to happen at the joining axis. So the electron density is lying on the joining axis. So again it is also a sigma bond formation. It is p to p overlap, right? So it is a sigma bond formation between two fluorine atoms. Only one bond can be formed as there is present only one partially filled orbital. Now the next one, here it is another hetero molecule is given, heteroatomic molecule is given. Heteroatomic means two different atoms are going to join to form this HF molecule. Here you have to mention the arrangement of both the atoms which are having the overlap with each other. Now this one is hydrogen fluoride molecule in which two atoms are hydrogen and fluorine. Hydrogen with electronic configuration H1 and fluorine with 9 configuration that is mentioned. Once again, hydrogen is having only s orbital which can go for the overlapping, while fluorine is having just one p orbital in the second shell, which will go for joining. So here s orbital from hydrogen and p orbital from the fluorine atom, they will join together. Here it is given 1s of hydrogen with the spherical shape and dumbbell shape of p orbital. They will give an overlap of the s and p orbitals, so it is an s to p overlap. Again, the central axis is having the electron density present on it. The both nuclei are present on the central axis. The pair of electrons localized. It is present on the electronic cloud is present on the central axis. So the formation of a sigma bond takes place here. Now you come to know that whenever there is S to S overlap, whenever there is S to P overlap, and whenever there is P to P overlap, every time there is sigma bond formation. Only one bond can be formed by hydrogen and fluorine in this molecule, as both of them hold just one unpaired electron with them, according to the BBT. Right? Now the next one is given. It is HCl molecule. Again, we have the configurations of hydrogen and chlorine. You can see chlorine with all the three of its electron, what to say, the orbitals that is shown. Hydrogen is contributing its s orbital, while fluorine is contributing its one of the p orbital in the third shell this time, right? All the three orbitals are shown for fluorine, and the s orbital of hydrogen along with its identity that is given. They both will overlap at the central axis. Again, the electronic cloud is lying on the central axis, the place where the joining the two nuclei occurs. So it is an S to P overlap once again with a sigma bond formation, as the electronic cloud is localized and lying on the central axis. Right? So this is the formation of HCl under the heading of VBT, that is valence bond theory. Now here another molecule is mentioned, that is oxygen molecule. It is homoatomic molecule once again. Oxygen is electronic configuration 8. You can see in this configuration each oxygen atom can contribute two of its orbitals. They are the p orbitals, while the third p orbital is holding a lone pair, right? Two p orbitals are half filled, so they will be arranged like this. These are the orbitals of each of the oxygen, first oxygen and the second oxygen. The only the orbitals which will have the bonding with each other, they are shown. If you want to draw the third one, you can draw it, right, with the bond lone pair in it, right? So it is given the overlapping of these two takes place, and overlapping of these two will occur. This will produce two bondings in it. One is present at the central axis, so it will be a sigma bond formed by the P to P overlap, while the second one is also a P to P overlap, but this time it is this lateral overlap which will occur to produce a pi bond. So we can say in oxygen to oxygen there are present two bonds represented by the two single lines, right? Now each representing a covalent bond. One of them is a sigma bond while the other one is a pi bond, right? Now on this way we say in oxygen molecule there are present two bonds due to the presence of two partially filled electron orbitals, which are each one is holding, right? Now the next one here, nitrogen molecule is discussed. You can see in nitrogen with atomic number 7, each nitrogen is having three unpaired electrons in three half-filled p orbitals, which belongs to second shell. Right? Now assemble them or join them like this. Each one is holding one electron in the each one orbital. Now here you can see only one orbital is lying on the central axis, right? This one. There will be three bonds will be formed over there. One by the overlap of the px to px orbital, the other one by p to py to py orbital overlap, and the third one by this one overlap will be there, and the third one will be the overlap of the Z to Z orbital, right? As all the three orbitals are holding one electron with each, right? G? So this one is what we say the overlapping will occur. Only one overlapping is going on at the central axis, that will be taken as a sigma bond, while the other two are lying above or below the plane. By means of the lateral overlap, they will give two pi bonds, right? Now remember it, the lines are shown above and below for the same orbit, means the px orbit, the lobes will join, py or pz orbitals, the upper two lobes will join together and the lower two lobes will join together to give a molecular orbital, right? So we say in nitrogen, when there is overlapping, there are three bonds which are present due to the presence of three unpaired electrons in it. One of them is a sigma bond while the other two are the pi bonds. Okay, do you understand? Now come to the next one. The next topic is hybridization. This hybridization also tells you about that of the formation of the bonds or the geometries under VBT as well. Right? Now here the hybridization. What is hybridization? The idea of hybridization was introduced by Pauling and Slater. This idea is related to the mixing of the pure s and p orbitals or the atomic orbitals to produce the new one orbitals, right? When it is same, just like to say that the mixing of the two colors, that is blue or yellow, it produces a new variety of color, that is a green color, right? So it is a hybrid one, the mixture of both of these, right? Similarly here you have to produce the orbitals. You know very well that the s orbital is of which shape and p orbital is of different shape. S orbital is spherical while the p orbital is dumbbell shape. When we will mix these two orbitals, we will have two new orbitals, right? Okay, now one thing more, the energy of s orbital is different than that of the p orbital. Shape is different, energy is different, but after mixing, what the new orbitals we get, none of them is like pure S or pure P, but both the orbitals will be of same shape and the energy will also be same, right? So this is what we call, that is hybridization, mixing of orbitals or intermingling of the atomic orbitals of different shape and different energy to produce new orbitals of the same energy and same shape. This is what we call is hybridization, right? Now for this purpose you should know that what the shapes of the orbitals are originally, and this is done only with that of the central atom. The bonded atoms around the central atom, they are not involved in that of the hybridization, but only the central atom undergoes hybridization before it goes for bonding, right? Now here we have the, it is what you say, as I told you earlier, it is an expansion of that of the valence bond theory. The different one molecules, they will be explained on the basis of this hybridization for their geometry. Now there are three types of hybridization depending upon the number of the atomic orbitals mixed. You can have sp3 type, as the name is indicating. S, one sp orbital and three p orbitals will overlap. to produce the sp3 hybrid orbital. The second one is called sp2 type, in which one s and two p orbitals will overlap to give three new p orbitals, and sp hybridization, in which one s and only one p orbitals will mix together to produce the new hybrid orbitals. There will only be the two hybrid orbitals. Now here comes sp3 hybridization. As I told you earlier, in sp hybridization only one s and three p orbitals, they are mixed together to produce. Now there are in total four orbitals which were taken for the mixing. So four new orbitals will be formed, as their shape is different, as their energy is different from the starters. So that's why they will be termed as the 4 sp3 hybrid orbitals. Each one is sp3 hybrid, right? The energy of the hybrid orbital is always less than that of the unhybrid orbital, right? Now here we have the produced sp3 hybrid orbitals. The ratio among them is 1:3, as the name is indicating that only one s orbital and the three p orbitals are involved. So you can say here 25% of each is contributing to that of the hybrid orbitals, right? Now sp3 orbitals, they arrange themselves in here there comes the geometry. These sp3 hybrid orbitals will assemble in the tetrahedral shape with an angle of 109.5, holding the electrons of the atom, central atom, right? Now here some of the examples are given which are explaining this type of. Now here it is given the overlap of the orbitals with the shapes which is being mentioned here. You can see s orbital with the spherical shape and all the 3p orbitals which are of dumbbell shape. When they mix together, they produce four new orbitals. Each one is now termed as an sp3 hybrid orbital, and if we collect them all from their smaller loops, so all they will arrange in the space in a three-dimensional manner. They will give a tetrahedral geometry. Now four will be assembled like this. Each one is having the difference or the angle between them of 109.5. So actually this is the shape which will originate when sp3 hybridization will occur in the substance. Okay, the central atom will hold four sp3 hybrid orbitals arranged in a tetrahedral manner. Now here the structure of methane, you know very well. Carbon with the 6th electron, it has been given. For this you have to write the ground state as well as excited state. This is the way that you have to present in the exam for the hybridization given in the methane molecule or whatever the other molecule is. So first of all, you should know which one is the central atom. As you are familiar from the Vesper theory, the central atom in methane is carbon. So only carbon will undergo the hybridization. Here the carbon with the ground state, 6 electrons are here with it. You can see here 1s2, 2s2, 2px1, 2py1 is the configuration, 2pz is empty, while it undergoes excited state as carbon. Everywhere you will find it with the 4 valency. So what happens? One of the electron in the valence shell will move from 2s to the 2pz naught, so that now in the valence shell there are present 4 unpaired electrons in the 4 half-filled orbitals, namely s orbital, p orbital at x, y, and z places, right? So this is called the excited state of carbon. Now all these will undergo hybridization as it is given on the previous slide, that 4 different orbitals, they will give rise a tetrahedral geometry when 4 orbitals are mixed to give. Now here the structure of methane is given. The 4 assembled sp3 hybrid orbitals are mentioned like this. For the carbon, the having tetrahedral geometry with them and the 109.5 degrees angle, the only overlap of hydrogen is required now. Here we have the 1s orbitals of hydrogen, which will each one will overlap with the central sp3 hybrid orbital of the carbon atom, and it will give the formation of a tetrahedral molecule in which carbon is linked with that of 4 of the hydrogen atoms, making 4 sigma bonds in it, right? As each one is having a central axis. Okay, so that's why we say methane in this carbon in the center will undergo hybridization, satisfying its valency of 4, and it will give rise a symmetrical molecule with a tetrahedral geometry and angle of the 109.5. Only the carbon will undergo hybridization. The hybridized orbitals will assemble in the form of the tetrahedral geometry, and each sp3 hybrid orbital now will overlap with the hydrogen atom to form sigma bond. So 4 sigma bonds are present in this methane molecule. Now comes this one. Here it is the structure of ammonia which is being mentioned here. According to its ground state, nitrogen with atomic number 7, it is having configuration. It is 1s2, 2s2, 2px1, 2py1 and 2pz1. Here the valence shell is the second shell. In it also the 4 orbitals will overlap to produce 4 hybrid orbitals. Each one will be the sp3 hybrid orbital. So ammonia is having nitrogen in it, and which undergoes sp3 hybridization. Here it is given, right? There is no need for the excitation as there is availability of the 3 unpaired electrons, all the orbitals at the second shell that they are occupied, right? None of them is empty. So all the 3 orbitals, namely s and p orbitals, will overlap with each other to produce 4 new orbitals which will assemble themselves in the. Now here the structure of ammonia is given. 3 of the p orbitals and 1 s orbital will overlap to produce 4 sp3 hybrid orbitals. Here the 4 sp3 hybrid orbitals of nitrogen are mentioned, which will arrange themselves in the tetrahedral geometry. One of the orbital which is present at the apex is occupied by the lone pair which is present in the outermost shell of the nitrogen, while all the other 3, as they have the 1 electron in each, will overlap with one of the hydrogen atom to produce a sigma bond with each, as the central axis is holding the electronic cloud for all the 3 as it is mentioned here. So the lone pair presence will define its geometry. It will be tetrahedral, but in this tetrahedral the only bond pairs will exhibit the particular geometry. It is pyramidal geometry which is given by ammonia due to the presence of a lone pair in its structure, and here the angle is also reduced as the lone pair is holding more influence on nitrogen as compared to the bond pair. So the bond pair will hold the less angle in between them. It will be reduced to 107.5 rather than in the regular tetrahedral shape that was 109.5. Okay, there will be 3 sigma bonds present in the ammonia molecule. Nitrogen is linked with 3 of the hydrogens. Each one is a sigma bond. Here we say these are the 3 sigma bonds present in it, and there will be present a pair of electron in the 4th one shell. So the geometry is pyramidal geometry and the angle will be 107.5. Now here comes structure of water. In water the central atom is oxygen with a ground state arrangement. It is holding 1s2, 2s2, 2px2, 2py1 and 2pz. One configuration, as you can see, it has 2 unpaired electrons in the p orbitals. None of the orbital is empty, but it will also undergo the type of hybridization which is called sp sp3 hybridization. 4 of orbitals will be mixed together. Every time when you are going to mix 4 orbitals, the same type of geometry is formed, that is a tetrahedral geometry will be formed for the central oxygen atom. In this case, 4 sp3 hybrid orbitals will assemble in tetrahedral geometry, but 2 of these orbitals will be occupied by 2 lone pairs, as they were present in the 2 of the orbitals of the oxygen atom, right? Now other 2 will hold 1 electron in each. Here it is given, this is the tetrahedral arrangement in which 2 of the bond pairs are given, that is when hydrogen is bonded with the sp3 hybrid orbital by means of an overlap. 1s partially filled will overlap with the half filled or partially filled orbital, that is sp3 orbital of the oxygen. It will be termed as sp3 to s overlap, right? Each one will have sigma bonding in it, while the 2 or the other orbitals, they are holding lone pairs in it. So the 3 types of repulsions are there according to Vesper theory: lone pair to lone pair, lone pair to bond pair, and bond pair to bond pair. These 2 will occupy more space on the central atom, so the oxygen atom will hold the geometry that is only given by the bonded atoms. It is bend shaped or V shaped or angular geometry, right? While the angle between them is reduced rather than being present in the regular tetrahedral geometry, it is reduced to 104.5. You can be asked a question that although water, ammonia, and methane all have sp3 hybridization in them, but their geometries are different. Now, the whole explanation is given. Think about that, why does it happen? Okay, the answer is lying in all these three structures given by these compounds. Okay, learn it well and ask if you have any query about it. Okay.